today's DevOps.com webinar. I'm Charlene O'Hanlon and I welcome you. We have a great webinar on tap today, as always, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of today's event, you will have the opportunity to listen to it later. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during our webinar you have a question for our panelists, please don't wait, don't hesitate, just use your GoToWebinar control panel and submit your questions, and we'll get to as many as we can near the end of today's webinar. Okay, with that, we will go ahead and kick off today's webinar, which is Distributed Tracing in Practice. Our speaker today is an expert in the field by all means. His name is Ivo, and he is the CEO and product manager at Plumbr. Hi, Ivo, great to see you.
Thank you for the intro. Welcome, everyone. So I guess as many of you today in the audience, I used to be a developer once. Somewhere I took the wrong turn and ended up in product management and now in the CEO role, in a company that's building application performance monitoring and real user monitoring products. But that's not the topic today, but while building those products, I understood that not just us, but all the vendors in this market rely heavily on what's called distributed tracing. So after being years in this market, I thought to share the insights of how distributed tracing can help you in your daily lives. So let's see what we have in store for you today. We'll start with the really basics. First, to understand what even triggers the need for the distributed tracing in the first place, and go over some really basic concepts. So if you're not yet on board with what the distributed tracing is, don't worry, we'll get you up to speed in the first few minutes. Then we move on to the slightly more interesting part, sharing examples in how distributed tracing can help you, and move on throughout a series of examples, from simple ones to some more complex one, increasing the power level effectively along the way. And at the end, hopefully sharing some insights to you how you could benefit from distributed tracing. Let's see some of the options or some different routes you could take when being interested in adding distributed tracing to your production servers. But as promised, let's check how the need for distributed tracing was even born. In order to have a distributed tracing need, well, you effectively need distributed services. And it effectively builds on two macro trends. First and foremost, you cannot really control innovation from top down. It's really the grassroots level innovation that fosters innovation in both small and large companies. And also the very same companies feel the need to innovate faster and faster. So even the largest companies are just forced to pick up chapters from the startup playbook and follow those or be outed from the business. So what does this really mean for the IT teams? Well, first and foremost, to support innovation at grassroots level means that 10 to 5 years ago, enterprises started moving away from good old monoliths to microservices, enabling innovation in individual teams. And in parallel to this move, DevOps adoption was gathering pace. So effectively bringing onto the stage a set of tools and methods to make sure that the innovation that gets built gets into production fast and without as many errors as humanly possible. So those two macro trends build the foundation for seemingly nice life. Your teams can innovate in isolation or in relative isolation from one another. And the result of this awesome innovation gets deployed in production in no time. So what can possibly go wrong with this? Many of you probably already know. Besides what used to be one stable big box, you now have a whole herd of microservices under your management. Besides just one single service, you now need to understand what's going on in few dozen of different services built on different technologies and released not monthly or quarterly, but instead daily or even hourly. So that builds the foundation for different issues to arise. Every change is dangerous by nature, And more changes means that you're just playing the game of odds. Every individual change can have just 1% of chance of bringing something bad to the table. But when you go through 30 of such changes, the chances of releasing something that's broken has increased to 25%. So it's not just when something bad is going to happen, but when it's going to happen next. And also the complexity of understanding what's really causing all those availability and performance issues has increased. All the dependencies between microservices and call stacks that can be up to few dozens of different microservices level deep make it really hard to find the needle in the haystack, to really find the root cause of your potential issue. So this has effectively built a foundation for both the distributed services and the need to somehow trace all those distributed calls now. And the problem that without the distributed tracing happens tends to manifest in different ways. But one of those can start seemingly innocent like this. A customer support ticket contacting your company and claiming that something in your digital services doesn't work as expected. Customer support escalates it to IT, it lands on your desk, and you start investigating. And this innocent looking email turns in just a few weeks into multiple email exchanges, trying multiple different tools to figure out what was going on and how to fix the problem that the customer was presumably facing. So that's one way of how missing distributed tracing can turn your otherwise productive work week into a chaotic trial and error. So that has set the landscape for saying hello to distributed tracing. So imagine that instead of looking at the complete mess, you would have an end-to-end trace for every request arriving at your distributed system boundary and capturing entire trace throughout every microservice that gets called during this request and links it into the original request. So as a result, you would have a visibility to the entire trace. And that's indeed what the distributed tracing is all about. A typical trace in almost all the tools I've seen and used will eventually be visualized similar to this, consisting of what are called spans, one span denoting the time or the individual outcome of the request to a particular microservice. And those spans get linked together in a timeline to form one single distributed trace. So how is this possible? The cornerstone of this, of any distributed tracing solution, is based on what is called universally unique identifier. So this is effectively a random number, generating of which requires no central coordination. If you remember, our system was distributed, and in such distributed system, it's hard to have the central random number generator to be used in such occurrences. So every node in this distributed trace is allowed to generate this universally unique identifier, and it's for all practical purposes guaranteed to be unique. To give you some idea how unique, for example, if you're not really afraid of being hit by a meteorite, then you shouldn't really be worried on your UUIDs colliding. So what goes on with these UUIDs that get generated? So let's assume a request arrives into a eShop. This particular request gets assigned a UUID that's visible on the screen, and the start of this trace is registered. As seen, it started after 7 p.m. Now this UUID gets passed along to the downstream node, in this case a submit order node. Now the submit order node receiving this doesn't start a new trace because it found the UUID already coming in from the upstream and just joins this existing trace. How is this possible? How do you pass along such UUIDs? Most typically, it is done by just passing it as a custom HTTP header. Most of the microservices communicate with one another using the good old HTTP protocol. So as seen in this example, which comes from our product, every vendor or every open source solution effectively adds their own custom header, which gets passed along across different microservices, which either start a new trace or join an existing trace if they already find such a header in the upstream. So that builds the foundation, generating the UUIDs and passing those along. And now each node participating in this distributed trace registers the time when the request arrives at the boundary of this node, and also registers the end timestamp, as seen in the last node in this trace, check inventory node. As seen, checking the inventory took 13 seconds. And it also registered the end result. It responded with HTTP 200 OK, meaning that the check inventory operation responded successfully. So that gives us the basic attributes for every span that gets linked into a distributed trace. They have to join or create a new ID. They register their start and end timestamp, and they effectively capture the outcome that happened within this node. In this case, an OK operation. So the responses get sent back upstream. The upstream node can register their end timestamp and send the response back all the way to the original node that received the request, that then sends the response to the client. Beautiful. We have captured our first distributed trace. Wasn't so hard, was it? Before we move on to the actual examples, a few more crucial elements. So who is capturing those spans, and who is composing the distributed trace out of those spans? So in order for any node participating in the distributed trace to be able to capture the information, they need to include something that's typically called an agent. That's denoted in the scary looking guys with hats. So every node here has attached an agent that captures the data and sends it to a central server. Such agents either can be introduced in the source code level, where the software engineer itself introduces the custom library to the dependencies and then uses the library code to build hooks into their application code. Or they can be introduced at bytecode level. For example, JVM or .NET Runtime can introduce such agents at bytecode level, instrumentation, or as last resort, you can use native code and via what's typically an LD preload, override some system level calls and replace those with your own calls in order to capture the information that you need. In any case, after getting this information by the agent, they now get sent to the single centralized piece in this equation. There has to be a centralized piece that accepts all the data that's now nicely captured by the agents, assembles it in order to build the entire trace. Remember, every node sent only a part of the trace. So now those traces get assembled and are made ready for querying and visualization. Let's look into those later down the road. And as an outcome, you'd get to see a distributed trace, which consists of spans. Every span registers its duration and the outcome. Out of those, the entire duration and outcome of a trace will be calculated. And also both the spans and the trace itself can be enriched with additional metadata, such as, for example, the user ID. So a distributed trace is composed, and we know what it is composed of. Besides, we learned that there is a need for one single centralized piece in the equation, and the agents have a role to play in this field. That has built us the groundwork, and we can now see how we can put those distributed traces into good use via different use cases. Just for example, we'll start with something as simple as removing the need to to reproduce or gather evidence when responding to support tickets, and then expand and understand how and whether we can actually turn it around, and instead of waiting for our end users to report bugs for us, maybe we can use the distributed traces proactively in order to expose the problems and respond to those before the users even call us. Let's see if this is possible, but let's start with simpler examples first. Going back to this hypothetical support case that we started with, John is writing us about the problem he's presumably having. I guess each and every one has seen the situations where those claims have to have actually no evidence anywhere in the logs, in the metrics that are captured. But let's see, maybe the distributed tracing will have us a different answer than what I see being used in situations where no distributed tracing is in place. So during those 2 weeks where the email exchange was going on, we see on average 6 different tools being used. And the most commonly used tool happens to be the good old grep, grepping through different log files, or in more modern days, you would use some sort of log analyzing systems, but borderline, bottom line case, it is still the good old grep. Different profilers being attached, heap dumps being done, garbage collection logs being analyzed. So effectively, the engineer responsible for the support ticket really needs to use all the playbook he has. But let's see if the distributed tracing was in place, and what would this response and then the use case for the engineering question would have looked like. So what if those distributed traces captured in their metadata include the customer identification? If we did that, then it's trivial to build a UI which is able to query those traces based on the user identification, which can be an email, as in this example, or a username, or anything for that matter. And now, if we would search for what John experienced during the time when he was presumably having some issues, we could indeed see that John has tried to submit an order. Submitting this order took him more than 20 seconds, and worse, it failed. And it failed in the charge credit card span, which took a long time and then failed out altogether. So that has removed us the need for, to actually verify whether what John was claiming was true, and allowed us, thanks to the metadata added, and also locate the source for the problem, at least to the precision of the span. So we know now that the charge credit card span is where we should be looking for the problem, not create order nor check inventory. The charge credit card span was what triggered the non-200 series response, typically a 500 series. So we have seen the first really simple example of how we could actually verify what the user claimed and zoom into the root cause, or well, not really the root cause, but quite close to the root cause. But as we see, we can do so much better. So let's see what this better could be. Let's go back to the very same situation where the submit order microservice was invoked by John, 7 p.m. on June 17th. It failed, but what if the distributed tracing solution at hand would also not just highlight the span that the error originated, but actually capture the error itself and link it to the span? And if the solution can do that, what if the solution can group the unique errors and quantify their impact? And in this case, we might see a situation where indeed we can verify that John experienced an error during the order submission, but he was the only one. He was the only guy who experienced the timeout exception during his order submission. So even though John really faced issues, maybe this doesn't justify the priority 1 response. Maybe it can be postponed over other most burning issues. So this is an example where if we would enrich the distributed trace slightly, then we are empowered to the way where we can really prioritize the individual incidents based on the impact that they really have for the end users. So we would be avoiding the what I have started to call a decibel-driven development. We can make sure that we respond first to the errors with higher impact and save the ones with minuscule impact to the later. But actually, this is only still scratching the surface. Let's see if we can go and expand the example. And we should expand it to zoom out to see what the user really experienced. So what if the very same trace we monitored starts not at the server boundary, not at the when submit order first reached our server farm was the first microservice touched, but what if we start the distributed trace already in the device that the end user is using? In this case, a browser. So as seen, John really made a user interaction in the browser, probably submitting an order. This started first by doing few static resource requests to the server. And then before doing a submit order request, which failed, it called to a microservice called check credit, which responded directly to the browser and didn't cascade through the submit order. So, and what if those microservices and the trace traversing through those microservices was also enriched with the errors that actually occurred in those traces? And we could see that, yes, John was the only guy who experienced a particular error in the context of order submission, but the check credit microservice has been broken for not just one user, but 150, at least in context of 150 unique distributed traces. So this might deserve a way higher priority, and the submit order itself could be just a collateral damage. So this is an example where the true impact of a distributed trace reveals itself if we zoom out to the level what the user is experiencing. So the lesson learned, and what's often forgotten, is that the distributed trace can and should leave the server rooms whenever possible. And the end-to-end trace is really the way where you can get a unified view of what the user experienced, and also make sure that they capture the impact of the root cause correctly. So we have learned of how we can use the distributed traces to verify the customer claim without needing to reproduce it yourself. We have learned of how we can prioritize the response by quantifying the impact of every individual error or bottleneck linked to such bans. And we have seen that if we go one level beyond the server room, namely, and attach our agents also to the device or into the browser that the real user is using, we can really capture the true impact. But it still boils down that John had to call us. Do we really need to wait for the John to dial up our customer support number? Maybe we don't. As a matter of fact, if those distributed traces are captured, they reflect the end user experience, both in terms of availability and performance. All such traces captured, aggregated together, really reflect what John and other users experienced in their devices now. So what if we would use this signal to alert you or anyone in charge for the particular production service in situations where either the availability or performance of the system degrades for your end users? And as seen in this particular slide, indeed, on July 30th, a particular release to one of our own production servers really spiked the error rate. What used to be beyond 1% of an error rate for this particular service spiked to beyond 6%. This was considered abnormal, and an alert was sent out, all based on effectively the distributed traces captured. And when this alert was sent to a particular channel, and when responding to the alert, thanks to the distributed traces, the particular errors were linked to the traces, and thanks to those traces being in place, we are able to see that even though there were 5 different errors impacting the users, just fixing the first one would have given us 2/3 of the impact, and fixing top 3 errors would have mitigated 99% of the outstanding impact. So it's quite easy to see here that you shouldn't be waiting for your customers to call or using any kind of proxy metrics to really learn about the situations where your users are suffering from availability or performance. Instead, what you can do is to rely upon the distributed tracing metrics to be the best signal to be sent, for example, either to your PagerDuty pages or to your Slack chats for your engineers to respond immediately. So now we have really expanded the case and shown you the ways of how you can really harness the true power of distributed traces. I hope now you have been seeing some use cases which could really simplify some of the problems you face in your daily lives. So if you're now excited to see how those different distributed tracing solutions can be adopted, let's look what's out there. First and foremost, I think I should start with that in 99.9% of the cases, I wouldn't recommend anyone to build their own distributed tracing solution. Having built one, it's actually slightly more complex in nuances than it looks on those slides. So unless you are at Netflix or Twitter level, you're probably better off of taking what's already built. First and foremost, open source distributed tracing solutions. There is quite a lot of them on the market. Most of them got the initial spark of idea from the Google Dapper research project published in 2010 and have taken it from there. So there are different varieties, but all of them follow the very same pattern. They capture spans, and those spans get some metadata, and those get aggregated in the server and then made available for querying and visualization. So that's one example how you could introduce, for example, Zipkin into your PHP application. So if you happen to have a microservices built on PHP, this is how Zipkin would capture, start a distributed trace and build a span. As you can see, this integration is done at source code level. So it's kind of creates a dependency with the Zipkin framework. But the captured trace really looks like a distributed trace should look like. That's a beautiful example of what you would get from Zipkin, given that you adopted it. With the open source solutions, it's of course comes without the cost that attached to commercial vendors, and this kind of approach is extremely flexible. You can add whatever metadata you want to the span. You can attach it to whatever programming language you need. The APIs are yours, so feel free to knock yourself out. But as a result, as I mentioned, you'll end up having a dependency with your application code and introducing a human factor. So if a newly built microservice author just forgets to add his service endpoint to the Zipkin monitoring, as we saw, you would have a blind spot in your distributed trace. And the usability of those central servers tends to be quite limited. So you won't get all the analytics you might need or might like eventually. So let's look at the commercial vendors. The commercial vendors, for unknown reasons to mankind, don't call distributed tracing distributed tracing. All the commercial vendors, Plumbr included, usually package this as application performance monitoring or real user monitoring products. But rest assured, all of them use the very same underlying concept. Distributed traces to capture the traces to highlight availability and performance issues. Those solutions typically take a less obtrusive path and attach themselves as seen in this particular example. This is a way how you would attach, for example, a Plumbr agent to your JVM. Just a startup parameter to however your JVMs get started. But the distributed trace itself that ends up being captured is doing the same that the Zipkin example or the open source examples does. with some enrichment in detail level, but that's already a nuance. So you'd get the same result. With commercial solutions, there is a cost side, of course, but there is slightly more heavy lifting that's done for you. So the installation doesn't involve any code changes, and you have overall less nuances to deal with. So if I were to tie it together, then I hope you now, those of you who didn't know what the distributed tracing was, are now equipped with the understanding of why this concept was born and how is it useful in the first place. And even more, I hope that the examples sparked some inspiration to how you can actually simplify your daily lives thanks to distributed tracing now at your fingertips. And also some sneak peek into how the different vendors can help you in this regard. And before I tie it together, being proud of every chef has to be proud of their own craft, and so am I. So Plumbr is one of the solutions I can recommend you to try. There is a fully functional 14-day trial of Plumbr, which you are all welcome to download and attach to your distributed shred races to see how we can really help you with all of the goodies that we covered today. We'll end up bringing you a single pane of glass across your entire service portfolio, integrate nicely with all the good things you already have in place at your house, and end up and all of this is still built using the very same distributed tracing that we discussed during today. Thank you.
Okay,
now
great.
I'm open to questions.
Lots and lots of time for questions here, guys. So if you have a question for Ivo, please go ahead and use your GoToWebinar control panel, and we'll go ahead and get started on the questions that we have. Let's see, the first question. How can you assemble all the different spans from all the different microservices running different technologies into a single coherent whole? Do you pass some extra information between your agents?
Yes, as we also discussed during the presentation, then all the nodes participating in this distributed transaction actually pass along the UUID that was generated in the first node accepting the request, or the first node triggering the request, depending on whether we are monitoring or not the device that the end user is using. So the HTTP headers pass along this UUID. This is effectively the only information you need to pass between your nodes. You can add some other if for some reason you need, but typically this is the only thing that gets passed along by all the distributed tracing vendors.
Okay, great. Then next question: how? And I think this is the question. It's kind of broken English here. How does Zipkin help on tracing without thread local storage?
So now, if I do understand the question correctly, then the question is about how does Zipkin make sure that the collected data ends up being sent to the central server without storing it locally for different situations. As we saw, Zipkin's approach is I used to call it obtrusive, but it's effectively approach is integrating at the source code level. So it boils down to whether or not the code sending it to Zipkin managed to send it, or maybe there was an error before it was sent, and or whether there is built-in framework that does store the data in situations where maybe the central server is not available. So it's up to the user to decide, really, in that case. Commercial solutions tend to buffer this locally, either per thread or in a more centralized location. But with Zipkin, it's really down to the implementer. I hope it helped. Okay,
great. Next question, do you have a solution for AWS Lambda-based functions?
Great question. Plumbr doesn't offer currently support for AWS Lambda monitoring. It's in the pipeline, but as of now, we don't have the support for AWS Lambdas.
Okay. All right, great. Next question. What is the memory and CPU footprint of the agent?
This is a fully legitimate question, and I hear this often from the customers as well. Because really, no monitoring solution should really make your application slower in the first place. That's really based on what the engineers have experienced with, for example, profilers. Attaching a profiler to a production server is almost a certain way to kill it. But with the APM vendors and the distributed tracing vendors, I think it boils down to first, of course, there is the real user monitoring side. Those libraries that do the monitoring in the end user device level, they tend to be loaded asynchronously over CDN networks and properly cached. So downloading this particular real user monitoring agent is unnoticeable for the real user. And then monitoring this in the real user device is also unnoticeable. And this happens within the single user browser, for example. There is not much usage. A human person can only click that much around in his browser. So in there is no visible impact. With servers, it boils down to monitoring the different system level metrics. In the need, there is memory, there is CPU, there is network overhead, and in some cases, even disk usage. And I'm proud to say that over the last 2.5 years, I'm yet to see a situation where customers taking us to a performance test run see more than a low single-digit overhead in any system level metric that they're interested in.
All right. Excellent. Excellent. Plenty of time for questions, folks. So if you have a question, go ahead and use your GoToWebinar control panel and submit it there. Our next question, do you adhere to either open tracing or open census specifications?
So I believe the question is whether or not the Plumbr is currently following those open source specifications. We are currently not. We keep a close eye of what's happening. I do believe that the future is in making sure that all the different vendors will open their APIs and make sure that they are coherent and matching the specification. This is really where the future is. But currently, it's really hard to make sure that those APIs are stable and whether there is a clear winner yet. So I'm keeping a close eye, but not yet.
Okay, great. Okay, next question. You may have to help me with this one, Ivo. The microservice like submit order will have UUID or how UUID is collecting here for distributed tracing. Can you please explain this a bit or a bit inside?
I'm not entirely sure I follow this question.
Yeah.
It seems to be asking the question of how the UUID is generated. If I interpret the question correctly, in the first node. So if it's a node in the downstream, then it gets the UUID from the upstream node. The agent just needs to check for whether or not the upstream passed along a UUID and then make sure it doesn't generate one, but just joins the trace with already existing UUID. But if the question was, how should I generate the UUID? There are awesome implementation of this UUID out there. I believe it's already the 4th generation out there. And if you Google for UUID implementation for your specific language, like UUID implementation for Java, you'll find awesome examples of how you can, for example, create your own UUIDs.
Okay. All right, great. Next question here. New Relic, better or Plumbr or Zipkin?
I would assume that each of them has their strengths and weaknesses. My background being from Plumbr, of course, my answer is that Plumbr is the best.
Yeah.
New Relic does some things differently than Plumbr. We do some things differently than New Relic. And so does an open source vendor, such as Zipkin, for example. So I can only encourage you to take out the vendors you might be interested in into a trial run and compare ourselves heads up against New Relic or whoever else you might have in mind. I'm fully comfortable that you'll be surprised of what we have to offer in good terms.
Excellent. Okay. The next question, is the agent only invoked when a trace request is made? With so many agents installed, we don't want things to consume resources when not needed.
So the agent, in sense, doesn't do any kind of background work. There is no background thread running, waiting for something to happen. The code that gets loaded is already instrumented during load time. So you don't end up finding any additional processes, for example, in your process table, or any additional resources consumed in situations where there are no incoming traces. So I hope it answered.
Okay. All right, great. Gosh, we're getting some really great questions. Next question, do you support gathering 100% of traces, or is a sampling algorithm applied?
This is what we do differently from most of the other vendors, and we are proud to say that we don't do sampling. Even with the biggest customers of us sending us billions of spans on an hourly basis, we haven't had to fall back to sampling in none of the cases.
Okay.
It's possible that probably if you approach us with a Netflix scale or Twitter scale data, then probably sampling is the way to go. But all the normal solutions, well, I'd say up to a few billion spans per day, don't need sampling with us.
Okay, excellent. Next question, which request tracing system would work best with Docker and microservices running on OpenShift container platform?
I don't think any of the vendors nowadays can really get away without fully supporting Docker and other containers in their various forms. So I'd say that it's more like pick a particular vendor because it supports a particular virtualization or a Docker, but don't pick the vendor who doesn't, because what I'm familiar with, everybody that wants to have a foot in the game has had to adopt all those beautiful means to deploy and orchestrate your production deployments.
Okay. All right. Great. Great. Guys, I think we still have about 10 minutes for questions at least. So if you have a question, please go ahead and use your control panel and submit it. Next question, do you think that after enabling distributed tracing, performance is degraded?
I think we kind of covered it already, but maybe from a different angle. Distributed tracing doesn't come for free. It is effectively additional CPU cycles that you end up burning, additional memory footprint, because you need to create some objects or allocate some memory to keep track of the different things, and you need some network bandwidth to now send the gathered data to the central server. So you'll end up consuming more resources. Now, a good vendor keeps it really at bay. As said, with our customers, everybody who has taken us into our performance run hasn't faced more than low single digits overhead in any system level metric being tracked.
All right. Yeah, I know that we have gone over that once before. So do you support different backends for tracing data, such as Splunk?
Nope. I believe it's where do we store the data? It's only currently just a single backend. The backend storage is time series data, which is effectively, this is where the spans and traces live, is stored in Druid. And we don't have kind of multi-storage capability for Plumbr servers. I know that some open source vendors try to become vendor neutral, but looking at if you have to query several 100 billion spans in real time, it becomes truly hard exercise even with one platform. So good luck with this exercise in going multi-platform. I'll try to support one and do it good.
Okay. All right, great. So we've gotten a couple questions in regarding GDPR and the personally identifiable information, and how that, how this solution might potentially collect. So can you kind of give us just a little bit of information about how the user monitoring works with GDPR and other regulations?
I think I understand the origin of the question, especially thanks to the examples I used. But now if we would, how to tackle this? Indeed, both Plumbr and every other distributed tracing solution can personally identify a visitor if this particular metadata is captured and sent to the central server. So this allows to identify the users and makes responding to the support tickets like we saw easy as we saw. Now, that being said, by default, we don't map the user to their personally identified identity. We don't map Mr. John Smith to their email. Instead, but by default, we make sure that we distinguish one user from another by effectively planting a cookie and tracking the cookie ID. But this doesn't identify the user, it just separates user A from user B, but we wouldn't identify the name of the user. So in order to enable the user identification, you'd have to effectively flip a switch explicitly. And then indeed, we would capture the user's identity, which is up to you to choose which we will map it to, be it a username or an email or something else. And this now might really take us to the GDPR territory. And now probably the consent that you would already be using, asking from your customers, does also need to explicitly state that Plumbr would be, or any other distributed tracing vendor would be one of the vendors that this information is shared with. Okay. But it's fully possible to capture, let's say, 85% of the distributed tracing potential without even entering the GDPR territory.
Okay, great. Okay, next question. What would be the recommended percentage of tracing spans that should be collected by the distributed tracing? It seems like 100% could kill the microservice at some point.
No good distributed, well, it depends, of course, on the service. I would assume that there are some services that are just outside of any standard solutions. For example, if it would be monitoring a real-time stock exchange, which, well, works at the sub-microsecond level latencies, so where the really ultra level optimizations are needed, then probably these solutions cannot be used. But everything that needs to work in human time, like where the times measured are in, at best, well, in few dozens of milliseconds, then I don't think capturing the spans is an overhead. And I would recommend not to sample, because what happens with samples is that whenever you have a problem and you're looking for the root cause for the problem, it's just some horrible law that says that, yep, those samples are sampled out. All those guys who faced the error that you would really now look the root cause for are just not within the samples you have collected. So by default, I don't really recommend the sampling route unless there is some clear reason for this.
All right, great. Gosh, so many good questions. Next question, is Plumbr available as a hosted version, or is there an on-prem version as well?
We offer both the SaaS version, which is the one we by default recommend that you don't have to install the server component yourself, but just send it to our SaaS servers. But indeed, if you want, there is an on-premise version of Plumbr where the server component sits in your server room and no data ever makes it to our way. So that's what typically the government agencies and banking and healthcare customers of us tend to use.
All right, excellent. Next question. With proactive monitoring, can Plumbr use APIs to create a ticket in Cherwell or ServiceNow?
Currently, from this product category, the out-of-the-box integrations include only Jira from Atlassian. So not ServiceNow or the alternative to this as of now, out of the box. But our API is free, and we do encourage to build those integrations, and or we can actually help you out thanks to our partners who would be glad to build those integrations, given that we'll start working together.
Okay, great. Great. We have about 5 more minutes for questions, and we have probably about 5 more minutes worth of questions here. So moving rapidly along. Can Plumbr cover Couchbase and Kafka tracing?
Now with those systems, it brings us probably to the asynchronous territory of not request response, but the publish subscribe. So in those cases, it's not so explicitly clear in human time, for example, of what's the latency perceived and when was the particular business process ended. So in these cases, out of the box, neither we nor any other tracing vendor can really match the messages in Kafka queue to a particular business process. So in those cases, our APIs need to be used. All of our agents have an open API, which can be used by the publishers and consumers of, for example, Kafka queues or topics in situations where you have asynchronous messaging in between your business flows. So you can keep an eye on asynchronous processes as well, but this doesn't come out of the box, and there will be kind of human involvement needed in order to use the APIs. You would need to show, well, effectively create the spans.
Okay. Here's a related question, I believe, that you may have already actually answered, but can we use distributed tracing as a plugin in CI/CD tools?
CI/CD.
Continuous
I'm not entirely sure I'm familiar with the category. CI/CD. Currently, off the top of my head, I don't know.
Okay, CI/CD is the continuous integration, continuous delivery.
Okay. Yeah. So if it stands for continuous integration and the release pipelines, effectively, if you have a nice continuous integration process in place and you have nice automated tests in place, then yep, Plumbr can be part of your release pipeline, making sure that the load tests running before the production release can be made doesn't contain any availability or performance issues. But this is not what we recommend for our users. It's quite easy to monitor this with other tools as well. And considering that you have control and reproducibility in your continuous delivery pipeline, then there is limited value that any of such solutions gives them. We don't say that don't use us there, but we don't really recommend that this is where the value is. It's really keeping an eye on the production.
All right, great. So I think we have time for one more question here. Let's see, have you any experience integrating tracing systems with the mainframe?
Unfortunately, or fortunately, depending how to look, nope. Haven't really tried that one, but I would assume that any open source vendor probably don't have the support for any of the particular code running in the specific mainframe, but they would have the data model and server and processing framework, so that if you would care to build the tracing for the spans originating from or landing at the mainframe, then you could expand such offerings. But I personally don't have the first-hand experience from there.
Okay, great. I'm going to throw one more question at you and then we'll close it out. Can you address vendor lock-in problems?
I would assume this comes from that if you have multiple different technologies in-house and now different teams would without the single distributed tracing solutions would use very different toolings to keep an eye on their portion of the distributed trace. So the .NET teams upstream would look through one dashboard, and maybe the JVM guys downstream would use different tooling, and there would be no single source of truth. So if this was the origin of the question, then I do think that yes, the distributed tracing solution makes sure that all your different technology teams stay and use the single pane of glass, and then share and use the same information to make decisions and solve problems, other than just arguing of who is right and who is wrong.
Right.
So if this was the nature of the question, then I think that's it.
Okay. All right, great. Well, that is all the time that we have for the question. So I do appreciate everybody who did submit a question. We had some really great ones today, so thank you so much. If we didn't get to your question for whatever reason, I apologize, but please know that the folks at Plumbr actually will get a copy of all of the questions, so I'm sure they'll be more than happy to follow up with you offline. I also want to remind the audience that today's event has been recorded. So if you missed any or all of it, or if you just want to watch it again, that's fine. You'll be able to do so. We will be sending out an email a couple hours after the end of today's webinar that contains a link to access the webinar on demand. And the webinar is also going to be living on the devops.com website. So you can always go there, check it out. Just go to www.devops.com/webinars. Look in the on-demand section, and it should be right there waiting for you. And while you're there, please take a look around, see if there's any other webinars that pique your interest. Ivo, thank you so much for a great presentation today. Lots of great stuff, lots of interaction with the audience. So I would call this a successful webinar. So thank you so much for your time.
Thank you for inviting me.
Great, great, great. Well, this is Charlene O'Hanlon, and I want to thank the audience for joining me today, and I'm signing off. Have a great day, everybody.